My name is Manuel Hernandez, and on behalf of my co-authors, Rashni Kaur, Maxime Korokov, and Richard Sowers, I'd like to present some work on the automatic identification of brain-independent components in electroencephalography data collected while standing in a virtually immersive environment, a deep learning-based approach. Our motivation lies in real-time brain-computer interface applications. We know that EEG has been used for monitoring brain activity in many prior applications, and thus automating an EEG signal processing pipeline is imperative to the exploration of real-time brain-computer interface applications. EEG analysis demands a substantial training and time for removal of distinct unwanted independent components, or ICs, generated via independent component analysis, corresponding to artifacts. We seek to establish a procedural way to identify and eliminate signal artifacts. However, the considerable subject-wise variation across these components motivates the finding a procedural way to identify and eliminate these artifacts. Thus, an automated approach would greatly facilitate IC selection and hence EEG-based research beyond trained individuals. We seek to develop human postural control enhancement technologies through an automated independent component categorization that would not only aid speed and consistency, but also assist online EEG processing for brain-computer interfaces to facilitate neurorehabilitation. Several studies have explored virtual reality and EEG-based setups to provide insights into neurocognitivity and adaptation. Virtual reality and EEG-based setups required real-time artifact rejection to develop novel acrophobia therapies and human postural control enhancement technologies. As an example, artifactual IC rejection might look as follows, where a combination of topographies as well as trial-over-trial activity and power spectral density would be utilized to be able to determine whether a component was cortical in nature or whether it seemed to arise from a art like a muscle. This can be evidenced by the high degree of high-frequency noise as well as the irregularities in the pattern, and the high weight coming from electrodes in the periphery of the scalp. Related works include the IC label classifier, which estimates 7 IC categories using deep learning with near real-time classification of online decomposed EEG data. However, there's still a need to continue exploring the application of machine learning to automate IC classification of EEG data from noisy, visually stimulating, and more real-world scenarios for future BCI applications. We propose DeepIC Virtual, a convolutional neural network deep learning classifier to automatically identify brain components in the ICs extracted from the subject's EEG data gathered while they are being immersed in a virtual environment. We examine the feasibility of deep learning techniques to provide automated IC classification on a noisy upright stance EEG data. Ground truth labeling of generated ICs were provided by a trained specialist and were done by looking at all 4 components of the IC representation diagram, whereas a convolutional neural network discriminates brain components from artifacts only by learning on one of the components, which was the scalp topographical map. For our experimental setup, we utilize a BrainVision 64-channel ActiChamp EEG system, EEG signal recording software OpenVive, the HTC Vive virtual reality headset, ForcePlate, and Python. The training and testing data for the study was accumulated from a design system with real-time EEG recordings set up while a subject stood quietly to pseudo-randomize height and depth alterations and induce perturbation. Study participants consisted of 5 healthy young adults, aged 20 years of age, and 1 male healthy older adult, aged 79 years, from the local community. 4 trials, each individually lasting for 240 seconds, with 8 pseudo-randomly ordered height settings, which include ground level, 2.5, 5, or 7.5 meters in height and in depth, included in the virtual world during each trial. During 2 of the trials, 10-degree toe-down perturbations were induced at all height levels, and subjects were instructed to stand still on the Neurocom ForcePlate while wearing the HTC Vive headset during the entire session. For data analysis, we carried out IC data generation, categorized types of ICs, and then perform IC classification. For IC data generation, real-time EEG data from scalp electrodes were recorded at 1,000 Hz sampling rate. The EEG signals, time-synced to the experiment in virtual reality, were then epoched into 1-second segments and processed via a bandpass finite impulse response filter to refine any noises. The filtered EEG, denoted by X, is a linear mix of source signals from 64 head cap electrodes, hence ICA is performed to determine weights matrix, W, and statistically independent components, ICs, I. The separating weights matrix, W, is computed such that the statistical independence between the components of I are equal to WX, is maximized over all invertible matrices W. An independent component representation diagram comprising of the following was used by the specialists. A scalp topographical map depicting positive in red, negative in blue, and note weights of the ICs on 64 channels indicated by black dots. A power spectral density diagram representing the power distribution of the IC's activity and event-related potential, and a time series illustrating a section of the IC's activity. ICs can be categorized as good, acceptable ICs, sourcing from the brain, and bad, removable ICs, further classified into 6 subtypes that are vital to eliminate prior to performing further analysis on EEG. Overall, we generated 1,637 label ICs with 285 brain, 149 muscle, 83 eye, no cardiac, no channel noise, 146 line noise, 769 other artifacts, and 205 hard-to-decide components. After eliminating the 205 ambiguous ICs, we retained 285 and 1,147 ICs classified as either good or bad components, respectively, with an imbalance ratio of 1:4. We identified components that are acceptable for EEG analysis, good brain ICs, from those which are not, bad artifactual ICs. Given the nuances in the ICs, significant training is required for researchers to carry out visual inspection and classification. Thus, advanced, deep learning-based investigations may be an appropriate approach for automating the IC classification task. IC ground truth labeling by a trained specialist was done by looking at all the 4 components of the representation diagram, whereas a convolutional neural network discriminates brain components from artifacts only by learning on the scalp topographical maps, without considering the other 3 components. 1,432 scalp images were colored and 135 by 165 pixels in size. Randomly stratified samples into 80% of the data for training and 20% for testing. 1,145 topographical maps were used in the training set with 228 good and 917 bad ICs. 287 maps in the test set were used with 57 good and 230 bad ICs. And a supervised convolutional neural network architecture was utilized to categorize good brain ICs and bad artifactual ICs. The convolutional neural network consisted of 8 convolutional layers with ReLU activation, batch normalization, dropout, and max polling. 2 fully connected layers with ReLU nonlinearities. The network was trained using the root mean square propagation, or RMS-prop, optimization scheme and the cross-entropy loss function. Xavier initialization assigned initial weights from a Gaussian distribution, and class weights were assigned to loss function, restraining the network from always selecting the majority class to boost accuracy. The classifier network was trained for 100 epochs with a mini batch size of 16 and with an adaptive learning rate initially set to 0.001. The prediction efficiency for the classifier was weighed via the test set confusion matrix, accuracy, F1 score, and area under the receiver operating characteristic curve, or AUC. The following represents our convolutional neural network architecture. Overall, the test set binary classification accuracy was 89.2%. We had an F1 score of 0.783 and an AUC of 0.926, with only 1 out of the 57 brain ICs being misclassified as an artifact. Overall, we see good performance of the classifier in identifying true positive cases. As we can see from the ROC curve, the convolutional neural network is able to do an excellent job of identifying good ICs. In conclusion, we attained an accuracy and AUC of 89.2% and 0.93 respectively, categorizing good versus bad IC topographical maps. Most of the brain ICs are known to be topologically coherent structures with connected broad cortical activities. Thus, scalp topographical information may provide sufficient data for accurate, automatic, and objective IC classification. These motivate further exploration on how spatial topology plays a role in such a classification task. Given the variability in artifactual ICs, these results will encourage clinicians to automate and study BCI methods to explore neural responses while in a visually immersive task. The entire data for the study was manually classified by a researcher, depicting the challenge of time and training inherent in such investigations. With the creation of DeepIC Virtual, we hope to lower the entry bar in terms of both knowledge and equipment while performing EEG and BCI explorations. Future works include the verification of the examined test setup for a larger and more diverse cohort involving subjects with motion-related disorders and over multiple experiments. We hope to use supervised transfer learning and multi-class classification methods to explore the efficiency of accurately discriminating the subgroups of bad ICs. Seek to examine the role of spatial proximity and connectivity of EEG electrodes in the IC categorization task, and investigate the addition of attention or weights to the network architecture. We would like to acknowledge all the participants in the study, as well as the Illinois Geometry Lab, Jump Arches, the William H. Chittenden Foundation, and members of the Mobility and Fall Prevention Research Lab who helped collect the data. And below are a few papers cited in the presentation. Thank you once again.